So my topic today is about, I began looking at renewable fuels a decade ago in 2004. That was before it was the thing to do. And particularly looking at renewable jet fuel, which is why you see a jet in the picture behind you. My university has the largest aviation school in the US, believe it or not. So it's kind of an unusual place for it, but there it is. And so I had a tie in there, and I figured, hey, maybe I can get some research money if I do something with airplanes. It didn't work out that way. I never got a dime through the aviation school of money, but I did get a pretty cool project out of it, and hopefully there's some lessons here you'll learn. I'm not going to go into the deep science. You can go read my published works if you want that, but this is going to be more about concepts and things to get you thinking about energy and things like that. So although the talk is about this biorefinery, the technology I developed, we won't get to that for at least probably 25 minutes of background stuff before we get there. So, and in fact, what we're going to do is talk about our motivation. For your society, I will be, as we like to say, preaching to the choir. You already know the motivations, but I will remind you of some of them, maybe give you some new words for you to use when you're trying to motivate other people about it. Talk about some of the other approaches that other people are doing. There must be at least a couple thousand researchers in the world currently working actively on renewable fuels. Believe it or not, they have different ideas on what to look at, and that's good. That's the way it works. And so I'll tell you about kind of some of those at the high level, not the detail level. Then we'll talk about my approach, which is non-catalytic cracking, which is a technology that comes out of the petroleum refining industry originally. I worked in a petroleum refinery for 7 years in Saudi Arabia back when I worked for a living. And so that usually gets at least one chuckle. It's okay, you know. You can go ahead and chuckle. You're supposed to, all right? So, but now that I'm in academia, I go into, there we go, that was better, renewable fuels. So. And then we'll talk kind of a bit, after talking about the fundamental concept of where we got to, then I'll talk a little bit about how you develop a process out of that fundamental research. Because research that just gets thrown out into the ether doesn't do anything. It's got to actually go somewhere, and then give you some concluding remarks. But of course, first, I have to tell you a little bit about my university and a plug. So be honest, how many of you know where Grand Forks, North Dakota is? Yeah, okay. It's all right. And that's because this is typically what you think the U.S. is, most of you. You know this city? If you go to the U.S., this is kind of the first place most of you would go. Notice I've changed my accent there a little East Coast accent. Yeah, but not only is New York City not representative of the U.S., it's not even representative of the state of New York. In fact, it's not even located in the state of New York. You can see it's crammed down on the bottom. It's actually adjacent to the state of New Jersey, not New York. But my relatives originally came from this part of New York, Buffalo, New York, which is on the other coast, which is where you get the phenomenon you have here called buffalo wings. Do you have that? Okay, so buffalo wings actually started as chicken wings in Buffalo, New York. And if you're from Buffalo, you never put the A in, so you can tell when a foreigner's saying it, Buffalo. So there's your first American insight. You don't have any things like that here in the UK, right? Yeah, so it's not even representative of New York State, which mostly looks like that, not like that, okay? And it's certainly not representative of this, okay, this big place here. In fact, I have never actually been to Manhattan. I've been to New York, the outskirts, but I've never been to Manhattan, and I don't feel very deprived, to tell you the truth. Now, for some of you, though, that's not where you've been in the U.S. if you've been there, or your vision. It's this. Right? And this is one of the two retirement capitals of the U.S. I actually grew up in the other retirement capital of the U.S. Who knows where that is? Oh, Arizona. Phoenix is the capital of Arizona, so yeah. So, and there's 105 golf courses in Phoenix. It's in the middle of a desert. There is no water. 105 golf courses, right? That's capitalism at work, yeah. So, but that is not even, it's fairly representative of Florida, actually. It's not too bad. There's enough retirees around to make the roads dangerous, and a few alligators wandering around, and I actually have a cousin that lives right there in Florida, and I have been there. But again, that is not representative of the U.S., so you're still like, where is he? Is he ever going to tell us where it is, right? So, all right, so I grew up in the state of Arizona, which is over here, which is why my accent is primarily what we would call California Standard English. Sounds a lot like the television. American newscasters learn to talk like this, pretty much. Okay. And then when I graduated, I went, boy, this thing's dynamic, to here, to Texas. Oop. I went to Texas, where I lived first in Austin, Texas, which is in the middle of the state, and then in Houston, Texas, which is on the Gulf Coast, and it's very hot and humid there. But that wasn't hot and humid enough for me, so then I moved to Saudi Arabia. And you say, Saudi Arabia, that's not humid. No, where the oil gets shipped out of Saudi Arabia is on a peninsula that goes way out into the Gulf, which in Arabia we call the Arabian Gulf, and on the other side they call it the Persian Gulf. And in America, we call it the Persian Gulf. So anyways, so the humidity level was ridiculously high, and so was the temperature. And so then I went and was, I had a transfer, and I was forced to move to Southern California. And then even worse, I was forced to move to Northern California, which is like paradise on earth. And then I left industry and went to grad school. Got my postgraduate degree. So I worked 16 years and then went that. And I did that back home in Arizona for all the good academic reasons, so my kids could be by their grandparents. And then when I graduated from there, I got one academic job offer because I had a problem. I actually had industry experience. Well, I wouldn't do any research if I had industry experience. Ooh. That was the kiss of death. So anyways, let's get on. Where is Grand Forks? There it is. Way up there in the middle. So I grew up, and you saw everywhere I lived was down here where it was hot. But now I live up in the upper Midwest. Have any of you seen the movie Fargo? Any of you? And I suppose that's your partner in the wood chipper. And it's such a lovely day, right? That is actually the way, it's a little exaggerated, but people up in that part of America, they do kind of talk a little like that. It's from their Scandinavian background. So in Grand Forks, we say we have a high diverse population. We have both Norwegians and Swedes. So, yeah. So anyways, that's where we are, way up there. It is the safest small city in America, 50,000 people. It is also the coldest city, small city. There's a colder place in continental America, not counting Alaska. The colder place is actually way up, very close. It's about 3 hours away up here, called International Falls, Minnesota. So you'll see International Falls will have the coldest temperature in the U.S. all the time. But it gets a little nippy there. So I'm looking forward to the Leeds winter actually being here. Yeah, so that's kind of what it looks like there. So the city's up there. This shot in the middle there of would you call that a stream? What would you call that little river? What do you call them here? Streams? So in the U.S. we call them either streams, creeks, or in this one little part of the U.S., which I didn't learn until I got there, they're called a coulee. Okay. Any of you have an unusual word for a really small river like that from around here? A what? A burn. A burn? Okay, yeah. Yeah, there you go. All right. And that's what it'll look like soon. They actually haven't had their first snow yet, but it's coming any day now. And this is what it looks like in the summer. So I actually lived on a property very similar to this one for when I first moved there, until I got tired of mowing 7 acres of grass and moved. So, but we're not here to talk about that. We're about to talk about the Department of Chemical Engineering. It is, and I will brag about it, but there is awards to back it up. We are the signature engineering faculty or school. I'm trying to translate here. We call a faculty a college and a school a department. So you'll hear those terms. So it is the signature department in the College of Engineering and Mines at the University of North Dakota. We have a boatload of departmental awards for both teaching and research. The teaching awards are primarily for undergraduate education. And then most of the faculty also have individual awards. So it's a good group. And certainly we push each other for excellence. At the postgraduate level, which we call the graduate level, we just shorten it, we leave the word post off. We have 5-degree programs, so it's not dissimilar to here where you have your chemical engineering and programs. So these are the 5 degrees that we actually we offer. And we do, all of our diversity is in the grad population. Very few undergrads that aren't either Norwegian or Swedish in background, an occasional Finn, Icelander, or German. But we get students from all over the world that come there to do their postgraduate work. All right, so, went the wrong way. We do have a number of student awards for their research also. We began at our university having university-wide awards for the best thesis, which is a master's write-up, or a dissertation, which is the doctoral write-up at our schools, in 2005. And they give one each year across the entire university. So if you count up how many you see there, you can see 50% of the time we've had a winner of one of the 2 awards. So that kind of speaks to itself as well. All right, so let's go on, get back to our talk, and we'll talk about our motivation. Just seeing if you're awake. Yeah. We don't actually have any elephants in North Dakota. We have some extinct mastodons, but that's about it. All right. So, of course, the motivation is why you're all here in this society anyways, and that's global climate change. This is a much harder argument in the U.S., where, believe it or not, public opinion is such that, probably almost half the population is very confused about the issue. Scientists are not confused at all, but about half the population has no idea anymore because they keep hearing stuff, lots of words from both sides. So I don't think you have quite as big an issue with that here in the UK. I could be wrong. If I am, let me know. But I'm sure you get some pushback anyway. So. But in particular in North Dakota, where I live, it's a very conservative state and very pro-business. And anything that smacks of a new regulation is verboten. You know, it's bad. So, but you know the argument. We've been putting a lot, and what you cannot argue with, though, is the fact that we've taken a lot of carbon that has been below the ground for a lot of years, and we've put it in the air. And carbon dioxide does have different physical properties and thermal properties than nitrogen and oxygen, right? Has a higher heat capacity. It has a higher radiative reflectance, right? And these things all do bad things for the environment. I think most global scientists now believe we are past the tipping point. Global climate change is now irreversible. At least in the short term. So it's going to be many, many years before the world can turn it around, but we have to at least start slowing down before we can turn it around. And so that's the challenge that you will face, youngins, because us old gray hairs, we didn't fix it. You get to fix it. Our predecessors left us tons of stuff to fix. We fixed some of them. Some of them we didn't know about, like this one. So you get to fix our mistakes. That's the way it works. And then your mistakes, you get to pass down to the next generation. Right? That's how it works. And that's why we need people to train the next generation of researchers, and we need the next generation of researchers. All right. Try not to hold it against us too much. So carbon dioxide emissions are truly a global problem. You can see that here. And what you should really astonish you here is that the industrialized countries where we all live, no longer produces the most CO2, okay? It's mostly produced now in the developing world, and China went screaming past the US in 2010 without just slowing down at all, just wham, as the largest emitter in the world. And India is very close to the combined EU 27 now. Okay? So if you want to deal with global climate change, you can't just deal with it in our countries. We have to look at global solutions, which means understanding what is important in those global societies. What is it that will allow them to move toward the solutions to global climate change? They won't be the same as here or in the US. Okay? There's different motivating factors. There's different issues they are dealing with. And we have to understand them and look for solutions within the context of what they're dealing with. Or they just simply won't go along with it. And there's nothing the rest of us can do. And nothing will get done. So we have to work with them, cooperate. But that leads them to an opportunity. Anytime we have to cooperate globally, there's a room for dialogue, better understanding across the globe, and that tends to lead toward peace rather than war. That's always a good thing. By the way, in case you can't see it, that's where the UK ranks by itself. It's currently just in the top 10, about to fall out of the top 10, as CO2 emissions in the UK have actually gone down rather than up, as they have in all of Northern Europe. Right. Okay, so talk about renewable energy. That's good because, of course, renewable energy can't solve the problem. So why work on it? Does this surprise you? Did you already know this? Renewables are not the answer. Okay? Look at, I mean, even if this projection from the Department of Energy in the US in 2008 is off by a factor of 10, we're not there, okay? So renewables in and of themselves will not solve this problem, will not allow us to displace all of the fossil energy that we use, okay? But it can be part of the solution, and that's why we keep working on it. So along with conservation and efficiency gains, the environmentally acceptable use of coal, efficient use of petroleum with gradual replacements to avoid economic disruptions, and that's a key for the developing world, and breakthrough technologies of the future. These are the areas like actual affordable solar energy, things like that. These are the technologies that we need. If somebody could figure out a way to safely deal with the waste from nuclear power plants, we'd be golden. Then we'd have an answer. But as long as we can't yet deal with it, it doesn't matter that it's a real small amount of waste if it's got a 10,000-year life, right? It's a leaky faucet with a bucket under it. Drip, drip, drip. The bucket will fill up. So we need these types of solutions in order to move ahead. And we have to work on all these fronts because there isn't another thing like oil, right? There isn't another one of those that we can just grab. Okay, we kept this one because we were waiting until oil was done. Oil's about done, let's go grab it. There's nothing there when you grab, right? So it's a lot more complicated, the problem's harder. That shouldn't surprise you. If you're working on research in your lab, recognize that your research will be harder than that of your advisor, your sponsor, your faculty member that's looking over your shoulder. You know why? They did the easy stuff, they left the hard stuff for the next guy. And we said the same thing about the generation before us. It always gets harder, more complicated, et cetera. Easy solutions get done early, right? All right, so let's look at some of the other renewable approaches. So are you motivated now? You okay? Anybody asleep yet? Not yet? Okay, good. All right, so first some practicalities. Feedstock costs are dominant, okay? It's actually pretty cheap to pull oil out of the ground, even with the harder to get oil that we have today where we're down 10,000 feet and running 5,000 foot horizontal stringers and fracking it. It's still much harder. It's still much cheaper than it is to grow this stuff. Okay, so feedstock costs are dominant, and that's why a lot of people are trying to look at, can we utilize waste better? Can we look at stuff that we don't really want to use for other things? In the US, we're spending a lot of time, because we produce a lot of the world's food, at looking at integrating fuel crops into the rotation. So we're not actually displacing food crops, which is one of the big myths, by the way. You rarely actually displace a food crop with a fuel crop. Food crops are just worth more. You just change your crop management practices to add them into the rotation instead of something else that was worth less. Farmers are great capitalists. They figure out what makes the most money, and that's what they're going to grow and keep their land going. So we do a lot of that. So feedstock costs are dominant. So the key is trying to convert as much of the inlet carbon into the final valuable, something usable as you can. Okay? And the other part about that is if you're not converting it into something you're going to use, where do you think it ends up? It's going into the air, which is what we're trying to avoid. So we want to use as much of that carbon as we can and put as little of it into the air as CO2 as we can. We have a huge investment in transportation infrastructure and in power generation infrastructure in the world. So the closer the renewable replacement is to its petroleum analog, the less costly it's going to be to adapt those systems to that system in the infrastructure. Okay? It's like, why don't we have a lot of electric cars? Well, there's a number of reasons for that, but one is you can't just go up to a filling station and plug your car in, right? They're beginning to come around and they're starting to put them in, but it's going to be a while. Okay? In the US now, in the upper Midwest where we are, where they grow a lot of crops that are used for fuel, you can go to the filling station and put biodiesel in your car, but only in the summer. In the winter, it's frozen, so you can't use it in the winter. But that stuff's slow and it's costly. It means that particular distributor had to put another pump there. Okay. Also, transportation fuels are much more valuable than syngas or electricity. So if you're making a methane replacement or you're making electricity, that's a lower value product than a transportation fuel. Transportation fuels have to be liquid, they have to have high energy density, they must be stable, and they must operate over a large environmentally dynamic range, right? So they have to operate in the winter, they have to operate in the summer. There are changes to the blends that refiners make, but it's not a lot. The basic components are the same. So it has to have a lot of dynamic range. That's why fuels are heterogeneous, by the way, transportation fuels. They're not made of one chemical compound. They're heterogeneous on purpose because it gives them that dynamic range. It gives us the ability that when I hit the accelerator, I have compounds in there that are good for that range, and when I'm at idle, I have others that are good at that range. Things like that. Increases the overall efficiency. Commodity chemical byproducts increase the margin and the product diversity, which increases the economic fidelity of a fuel plant. Petroleum refineries are enormous, and they're incredibly efficient. There may be no more efficient industry in the world than petroleum refining. The margins are very, very low. And because of that, that's who you're competing against with a brand new technology. It's very hard to do. So you need something to give you an advantage. Plus, those petroleum refineries are also producing lots of byproducts that have more value than the fuel. So if you don't have them, how are you going to compete against them? Okay. Now, but when you're talking about byproduct chemicals here, you can't be talking about, say, an ingredient for a pharmaceutical, like a new antioxidant. Okay. One plant will provide the world's supply. What are the other 990 plants going to do? Right? They can't make that one because the market's saturated. So you need high volume commodity chemicals, which drives you very much to polymers. Right? Polymers are ubiquitous in society. They're everywhere. You're wearing them, you're sitting on them, you're seeing through them, everything we do, we use polymers now. It's the biggest market we have. And almost all of those are made from a fossil fuel, okay, with a few exceptions. So that's a place to look. And the other ones are some other things like lubricants and various other things. But you need high volume byproducts. They don't have to have huge markups, but they got to have markups that are better than fuel so you can compete against the petroleum plant. And of course, you want your energy and water usage to be minimal. All right, there's kind of two basic strategies that researchers are looking at and have been ever since we started in this game. biochemical and thermochemical. Okay? So in the biochemical way, typically one way you're doing that is you're breaking down the biomass perhaps into something that's accessible to whatever the organism is, whether it's algae, yeast, bacteria, and typically the first ways that has been done is with sugars or carbohydrates. There are other technologies where people are working on now. But in any event, that becomes, so your bioresource, your biomass is the carbon source, the primary food for that organism. That organism munches it up and expels it as something that you can use. Okay, so it makes a more complicated carbon or a carbon in a form that you want it, and you can use it. Thermochemical conversion, basically where you're going to use heat and possibly pressure. We may facilitate it over a catalyst or we may not. And we're going to break it down from some complex carbon form into a simpler carbon form, and then we're going to turn around and take that carbon form and we're going to further process that into our final products. Okay? It's kind of the two strategies. Pretty much everything fits into one of those two categories. Of course, there are exceptions. With 1,000 people looking at this, there's always exceptions. But these are the simple ones. The first generation fuels come out of those two camps. So ethanol from corn, which goes into gasoline engines, is one of the two commercial first generation fuels. And the second one, biodiesel, is basically a thermochemical way to do that. All right. So those are the first two that came out. They have some clear limitations. Ethanol isn't really compatible with gasoline. One's polar, one's non-polar, right? You really have to work to get them to want to mate together. I mean, at small concentrations, they're fine, which is where the limits you see on them, right? E10 and E85 are the limits. That's the solubility limits, by the way. You can boost those up a bit by putting in some expensive additives and other things, but of course, we'd rather not do that. There's also energy density problems with ethanol, so you won't get as much per volume of fuel that you put in your tank. You won't go as far. And the energy transformation efficiency for ethanol is fairly low. Okay, there were a lot of arguments when it first came out that it actually took more energy than you got. I think most people are convinced that it's probably about a wash, but it's not that efficient. And of course, if you're making it from corn, you are competing with food and you have feedstock availability issues, although the market does adjust to a lot of those. When I moved to North Dakota in 2000, the corn line was about 80 miles south, almost to the South Dakota border. The corn line is now up into Canada. That's how far north is it still profitable to grow corn? Because corn is a longer growing season, so and you can grow it longer for fuel than you can for food because you can let it freeze. So you can do that for cattle feed also. If you're going to feed corn to livestock, you can let it freeze and then you just harvest it after it's frozen, and you can do that for fuel. You know, if you're going to eat corn, you don't want it to have been frozen on the stalk. Believe me, it doesn't taste good. So considering it, we've already had freezes in North Dakota since probably early September. It's a much shorter growing season. So anyways, biodiesel, there's cold flow limits. So forgive my using Fahrenheit, but at 0 Fahrenheit, biodiesel is a solid. So 0 Fahrenheit. And in North Dakota, where in January the average high temperature is -4 Fahrenheit, that's a bit of a problem. You wouldn't believe what farmers do in North Dakota to try to use biodiesel all winter in their vehicles because they're committed to it. They will actually mix it with regular diesel number 1, which is almost kerosene, in November and put all kinds of stuff in it so it won't freeze, and put it in heated tanks and have heated tanks on their trucks so they can use it through April. So it also has energy density issues and stability issues. Typically the shelf life of biodiesel is about 6 months because we haven't gotten rid of all the oxygen in it. And so it will start reacting and form oligomers, which will plug up the filters and all that. Right, so if those aren't any good, we need to make something else. What we'd really like to do is we would like to replace the 3 building block transportation fuels that come from crude oil. That's gasoline, kerosene, and diesel. Kerosene is primarily used for jet fuel, and it's also used for cold weather diesel. The cut line there is kind of, you can argue which way it goes. But here's the thing. When a petroleum refinery was built, and at least in the US, a new refinery has not been built in over 40 years, okay? They are configured for a certain ratio of these based on the crude stocks they anticipate having. And the units in a modern petroleum refinery, we're talking 40, 50 billion pounds to build that thing, okay? So you don't just throw it away and build another one. First of all, you'll never get a permit. And secondly, it's just too expensive. So you can adjust it about 5%. That's about all you can change the lineup, about 5%. So think about what that means. When ethanol entered the US gasoline market, and gasoline is the dominant transportation fuel in the US. In Europe, it's about 50-50 gasoline diesel, but in the US, it's 95% gasoline. Diesel is almost exclusively for trucks, okay? So when ethanol went in the market, what do you think happened to the price of gasoline? Did it go up? Of course not. It went down. It went down because the refiner is making gasoline. He has to make gasoline in order to sell diesel and kerosene. He can't not make it because he's going to get essentially the same ratio. He'll adjust it as much as he can, but he's going to make it. So supply goes up, price goes down, okay? But remember, he works on a margin. He buys his crude oil, he sells his products. That margin is his profit. If he decreases the price of gasoline, what do you think happens to the price of kerosene and diesel? They go up, okay? All right, biodiesel enters the market, okay? Not nearly as much biodiesel as ethanol, so the price of diesel is depressed a little, but the price of kerosene goes up more. Okay, here's the data. So around 2003, the wholesale delivered contract price of these 3 fuels was essentially the same. See that? In 2008, look at now. See the gap at the bottom? That's what I call the ethanol gap. So that's what ethanol being introduced to the market did to the prices. I heard somebody just the other day say, even here in the UK, do you remember when diesel was cheaper than gasoline, than petrol? Remember that? All right, you weren't born yet, but just kidding. So it's going like that. The poor airlines, they're the ones that are really getting it, because nobody's going to run a refinery to make jet fuel. It's the smallest of the 3. So I'll tell you, if we could completely replace gasoline and diesel, we'd better have something for the jets, or air traffic will come to a halt. Now in the UK, that's not as big a deal for you. You have these things called trains. But in the US, where you take a train, we fly. Because for you, going all the way across the country is a what? 6-hour train ride? For us, going all the way across the country would be a 40-hour train ride. Okay. And where I live, it's a long way to anywhere. It's 6.5 hours to the nearest large major city, million-plus city. Okay. 6.5 hours. You're in the ocean here. Okay. So this is not insignificant that this happens. So what that means is we got to make sure we don't just solve one problem and just create others. Okay. So we got to be mindful of this. All right. Thermochemical processes. This is kind of the typical way some of these work. This one's from the Department of Energy site. This is kind of their concept. That basically you gasify the carbon source down to its simple components. You make methane, hydrogen, CO, and then you build them back up into whatever it is you want. Okay? It's good for making a synthetic natural gas, by the way. Gasification is great for that. It's very efficient. It's a good way to do that. It has some issues, but it's not bad. But it's really difficult to rebuild longer carbon chains. It's very inefficient and very expensive. And hence, this technology is stuck at that last box, fuel synthesis. Okay? Because it's just really hard to do. The best process that's been developed for this was developed in World War II, believe it or not. It's called the Fischer-Tropsch process. It was developed by the Germans, who had no more access to petrol. And so they developed it. They knew it wasn't a real good way to make it, but that's what they had. And so they did it. And that's still the best way today. Nobody's beat it yet. And there's a lot of people trying, I guarantee you, to do that, but not yet. So this is kind of like, well, okay. It's hard to build carbon chains up. So, but do we have to really gasify it all the way to methane? The answer is no. And we can do what's called fast pyrolysis. So a fast pyrolysis unit basically is a bad gasifier. You just decrease the residence time a lot so that it's only in the gasifier, the combustion unit, for a short period of time. You do it without oxygen. And all you're trying to do is partially break those bonds. You just want to break a few of them, not all of them. Okay? And then this was kind of the original concept. You do that, everything comes out of the top as a vapor, or it's a char. You collect the char out of it, which you can use for all kinds of things. And then you take that vapor to a condenser, you condense all those big molecules down, and now you've got bio-oil. We're in business, right? Wrong. That oil is the nastiest stuff you've ever seen. And depending on what you've made it out of, it may not even be an oil. It may be an emulsified goop. Okay? Because there's enough polar stuff in a lot of it that it'll emulsify into a big goop. Any of you ever made any of that in your lab? Made some goop? Yeah. Easy to do. And there's all kinds of nasty stuff in there that is carcinogenic, smells really bad, it's really hard to burn. I mean, you just can't use this stuff. So a lot of people then have been looking at how can we upgrade that bio-oil? Some of them right here, right? Okay, what can we do? How can we do it better? Okay. Well, the concept that seems to be most reasonable, I'll say that because I'm one of the people that thought of it. I'm not the only one, by the way. There were a lot of others. Is called stage condensation fast pyrolysis. So when we come to this part right here, let's not cool the whole, condense it all. Let's condense it in stages. Let's take the heavy bits first, then we'll take the next bits, then we'll take the next bits, all right? And so we came up with that concept, independent of two other groups that came up with it at essentially the same time. This is what our unit looks like, and so if you see, ours are just as ugly as yours units that we make, all homemade, made by students. So the oil and biomass get ground up. We go into the fast pyrolysis unit. Stays in there about half a second. And that's this part right here on the diagram. And then we come out of there and we're going to go into the second section, which is the 3 condensers. So we have a condenser and a collection pot, condenser, collection pot, 3 of those, and then the gas out the back. And if we wanted, we could refrigerate that baby down and get even more stuff out. What you find when you do this is you'll get this really nasty stuff. The real heavy stuff that you don't like mostly comes out in the first cut. The middle stuff actually looks pretty decent for processing into transportation fuels. It's actually workable. And then the light hydrocarbon water mixture, all the emulsifying agents were in the heavy cut. So now they phase separate and you can do stuff with them and use them. So it looks like a pretty attractive concept. The heavy ends, what our concept is, this is kind of one way you could do something like this, is to take those heavy ends, take and separate out the aromatics and the tars from the kind of the longer chain hydrocarbons, crack the oil, take the tarry stuff and coke it, crack the oil and coke the tar stuff, and you can get a really nice carbon product, very pure. Because if you make this from a biomass, all those metals and things that are in coal and petroleum aren't there. So it's actually a really nice, clean, high-grade, anode-grade coke, which is used for all kinds of things, anodes and other things. Middle distillates, you knock out the heavies and the lights that are still in it because we just did one crude condensation. Then we can deoxygenate it in a number of different ways, and then probably do one trim purification, and we should have our products. Okay? Or a series of purification, separation units, distillation, but stuff that's easy to do and we know how to do. That's the good stuff that we'd like to make in a product. And then the light ends, we can recover some naphtha out of that to make a naphtha product. We can make propane, butane, what's known as LPGs, and then the syngas we can send to the boiler, and we can even shift some of the CO and make some hydrogen if we want to use that for our deoxygenation. So that's one concept of how you might do that. All right. Going to the biochemical, I'm running way late, sorry. Oh well. Fermentation alcohols, of course, was the first way this was done with yeast. There are now, but that bioreactor can also be bacteria, it can be algae, and there's lots of different things that people are suggesting in trying to do that. That's not really my area of expertise. I will say this about it. Although some of these are fairly intriguing, they're probably better for chemicals than for fuels. And here's why. They usually make one thing, so you have purity on your side. Purity is good for chemicals, bad for fuels. Dynamic range, remember? Secondly, bioprocesses are inherently less efficient than chemical processes. You've got to deal with running at least semi-batch in operation. You have to keep things alive, so that gives you kinetic limits on temperatures and pressures and things like that. And so they're never as efficient as chemical. So if there are two solutions that look equally viable, and one's chemical and one's biochemical, the chemical one will almost always be better commercially than the bio. It's not 100% true, but it's usually true. Right. So the main way that people are making jet fuel and diesel today, this technology is actually coming to the commercial scale right now, and that's hydrotreating or hydroprocessing. This is the UOP version, which is the one that is most common out there. Your feedstock, which is a triacylglyceride-based oil. Triacylglycerides are made by crops. It's a glycerol background with 3 fatty acids on it. Okay. So you, as a mammal, make fatty acids, free fatty acids. That's what that is, right? But most living things make triacylglycerides instead of free fatty acids. So they're made by all kinds of things, bacteria and algae and lots of plants. It's amazing how many plants make these things. Every time I turn around, I'm finding another one. Anyways, that's the feedstock here. You go into the reactor. You blast it over a catalyst, which will knock off the backbone, deoxygenate the acid group on the fatty acid, and some of them also isomerize, or they'll do that in a second step, so that you get this dynamic range and mixture, and you come out of there with a reasonable jet diesel cut. During the separation process here, some of that will crack. It naturally will crack, and they'll get some light ends on top of that. That's the process that is mostly going into the world today. All the airplanes that are flying green jet fuel today are flying hydrotreating fuel today. Right now, their limit is 50% of the fuel. And there's a reason for that, which I won't go into because we don't have time. You'll just have to figure it out. All right, let's talk about my stuff. So our stuff is non-catalytic. It's thermal cracking. So instead of hydrotreating, we're just going to pyrolyze. So it's just like pyrolysis, except the conditions are slightly different. We fell into this. I had a post-grad that I didn't feel very confident giving him a catalytic reactor with. So I said, let's start with non-catalytic, and if you can do that, I'll let you do it with a catalyst. We never got to the catalyst because it works so well with the non-catalyst. I had subsequent students look at it both ways, and what we found out was that catalytic cracking isn't actually catalytic cracking for triacylglycerides as it is in hydrocarbons. It's actually non-catalytic cracking with secondary reactions occurring on the catalyst. Okay, so you can do those secondary reactions all in one step, put the catalyst in the reactor. That means when you form tars, it gets all over your catalyst. Or you can separate the two steps out, do the non-catalytic cracking, recover the tars, put the non-tarry stuff over the catalyst, and do what you wanted to do with the catalyst separate. Your catalyst will last longer, and you've also recovered the tars instead of turning them into CO2. That's the advantage of this process. Okay. It produces drop-in compatible fuels. The fuels meet the petroleum specs, not the hydrotreating specs. To meet the hydrotreating specs, we would remove the aromatics that are in it, then turn around and sell them back to the airline or the fuel company so they can blend them back into the hydrotreating fuel to make a full fuel, which some of them do. And it's based on this premise that it's easier to break things than to build things. So we let nature do the building. Nature's been doing it a long time, does it real well, and nobody's figured out a real good way to build the bonds yet, so we'll let nature do that, and we'll just break them. But we'll break them the way we want. Turns out it's really predictable, and it has to do with the bond energy, so this is the only science you're going to see today. But basically, the backbone comes off real easily. These bond energies are real low. And then you'll see the next best ones are near a double bond. Okay? So if you have a saturated fatty acid with the only double bond being here on the end where the carboxylic acid group is, it's just going to knock that carboxylic acid group off. And you'll get acetic acid and a long hydrocarbon. If you've got some double bonds, though, in here, it will break in other places. And it's repeatable and predictable. And you can tell, based on the fatty acid composition, what you're going to get out. Okay? Now, I say that even though that's what you get. Look at the complexity there. Okay? It is repeatable and predictable, even though you're getting 300 plus compounds. Okay? Given the exact same fatty acid composition, I can crack it multiple times and I will get the same profile within the limits of analytical accuracy. Okay, so it is predictable and repeatable. So you make a diversity of things. That's good for fuel, not as good for chemicals. But you make some interesting things. You make a lot of carboxylic acids. Turns out they're almost all alpha carboxylic acids. You make a lot of olefins, and the linear ones are almost all alpha olefins, which is also good if you want to make chemicals out of them. And you'll notice there's the aromatics that I said you have to remove otherwise. You see also where this is. Now, most triacylglycerides are primarily centered around C18, C20, and that's why when you break them apart, you get a lot of C7s through C12s. That's the sweet spot. That's what we want. That's middle distillates. So that's why we like this. So we can use all kinds of different oils. We're going to make fuel, and we can make some chemicals out of the short-chain fatty acids and the aromatics and carbon. We've identified a lot of things we could make, and we focused in our lab on about 45 of those, actually demonstrating them. The basic scheme is you put the oil in the reactor, break it apart, you end up with light, non-condensable light fraction, middle distillate fraction, heavy fraction, separate them out, treat each one separately and get your products. So this is, we've run a lot of different oils. So here's a suite of 6 oils we ran, and you can see that it's fairly consistent in composition. You get mostly jet fuel if you want to run it for jet fuel. You can crack it differently to make more diesel and naphtha, but notice that the gases are very low. And that's good. You don't want a lot of gas because, again, syngas isn't worth as much as the fuels. We can predict the influence. We've done enough runs now and have models. We've run hundreds of cracking reactions of everything imaginable. So we can actually predict what the effect of a different fatty acid chain in a plant will be. So we've actually worked with Bayer Crop Science to look at some of their non-edible crops like camelina and some high uricic brassicas to actually genetically, or not genetically modify, naturally mutate those crops toward having the types of fatty acids that increase the yield of the fuels. Right. So why do we want to do it non-catalytic? I've kind of said this already. Catalysts will foul the catalyst. In a petroleum refinery, you have good metal catalysts. They're robust. You can fluidize them, send them to a regenerator, burn the carbon off to CO2, put them back in. Here, you're primarily looking at zeolites or silica alumina-based catalysts. They're not nearly as robust to do these catalysis. Or some of them are platinum on carbon, very expensive catalysts. In any event, if you put if the catalyst is in the bed, the cars will gunk up the catalyst. You will have to burn it off. And so that's up to 10% of your inlet carbon that's going up to CO2 that in our process we actually recover. So if you design your reactor right, it's not going to plate out on the reactor. You just have to design it right. Also, we get a better diversity of byproducts, so we can make better things than you can from a hydrotreating process. And we can accept dirtier fuels or feedstocks, and again, that has a lot to do with the fact there's no catalyst in the first bed that a lot of things like cellular debris and stuff tend to cause problems with. And so in ours, it's not in the first bed. All of that goes out with the tars. And so it's a little nicer process. And so for biological oils like algae and bacteria-based oils, there's a clear advantage here. One company that's doing biological oils from bacteria told us that it's worth up to 25 cents a gallon to them. So it's a pretty big, that's a huge amount. There's some data on crude and refined corn oil. So we went to the ethanol plant and pulled out their corn oil at the end of the plant where it's been all beaten up and got all kinds of stuff in it. And we ran food grade oil that you'd buy at the store, and you can see the results are basically the same. We did that also with a crude bacterial derived oil. Comparing that with soybean and canola, you can see, again, about the same. So it's not even the refined stuff, just the crude stuff. Byproducts can have a significant cash flow value, and they de-risk your product, so you'd like to do those. So the ones that have the most value for us are the short-chain fatty acids, C2 through C10. There's a lot of uses for them. They're big market ones. They're easy to get. And so I'll tell you about that in just a second as we move now into process development. So the basic concept, cracking, but now you got to develop a process for it. So I'll tell you a little bit about that. So this one's for you, Andy. This is an American analytical chemist, obviously. I was in Tombstone, you know, the OK Corral this summer, so it's quite hot. So here's the process of developing stuff. You got to invent the basic concept with exploratory research. Then you do the applied research to actually get it reasonable. Then you've got to develop it, which is to get it basically data that would make it amenable for commercialization. And then you got to scale it up. So that's the pathway you have to use. So our concept is the fatty acid biorefinery, multiple feedstocks, multiple products. You can feed it any or all of these. You can mix them, blend them. It doesn't matter. Once they go in the cracking reactor, it really doesn't care. The conditions for cracking are slightly different depending on the feed, but not a lot. It's just, you know, maybe 5 degrees different up or down. The product mix will be different coming out the back, and you can make lots of stuff. The basic process, we went through this before, but some other things that you can do. There's a lot of propylene that we generate. When we break off the glycerin backbone, we don't make glycerol, unlike these other plants. Like a biodiesel plant, you get tons of glycerol, right, when you break that glycerin off. Instead, we make propylene. Okay. Well, propylene is good. You can make aromatics from propylene. We make ethylene, butylene, and so those three we can feed to a reformer and make some aromatics. The middle chain, we can extract the fatty acids. We found a tertiary amine that will extract about 99.9% of the fatty acids that are in the liquid product. And so then you can recover the ones you want. Any of them you don't want, you can just either decarboxylate them or you can transesterify them, either one, and just throw them back into the fuel pool if they're not worth actually selling. And if you want to get the aromatics, we use sulfolane. That's the exact same way that aromatics are extracted in a petroleum plant. It actually works fine in this as well. Okay, and then we got the heavy ends. And what we do with the tars, this one has been fully developed. We can take the cars and we can basically coke them into anode-grade coke. Okay? But the one we're still working on and the one we're most excited about, this is an alchemist's dream, making mesophase pitch for carbon fibers, continuous carbon fibers. So that is a very high volume, very high value byproduct if we can make it. In fact, you would run the plant to make as much tar as you can if you can make the carbon fibers. We're pretty close. We're still getting discontinuous carbon fibers out of it, but we're getting close. I think by the end of this year, I think we'll be there. Right, so how does this look commercially? This is what we project. So if we have a 50 million gallon per year fuel plant, which is kind of a typical standard DOE comparison size that they use, this is what you're going to make. You put your oil in. This is all based on soybean oil, but it could be other oils. You're going to get about 25% jet fuel, 34% diesel number 2, 12% naphtha, and then some nits and bits. 84% conversion efficiency. The most we can get is 90%, okay, out of ours. That's the theoretical maximum. The rest is going to CO2, no matter what we do, once you deoxygenate the carboxylic group. And it takes about 14 kilowatts per gallon of feed, and there's no external chemicals. There's no external hydrogen needed like a hydrotreating plant. Here's what the costs look like if you had 25 cents a pound feedstock oil. It's about double that right now, so I'll show you those numbers in a minute. But it costs you about 31 cents per inlet gallon. These are the slides I told you about that I don't want you to put in the final. And you can see there, at 25 cents a pound, you're going to make about 40 cents an inlet gallon. That's about what you'd need to make this profitable. Now, if we extract the short-chain fatty acids and use those, the conversion efficiency goes up because we're not removing all those carboxylic acid groups anymore. We're keeping a lot of them. So the efficiency goes up to 87% out of about 93. Energy usage goes up a little bit, and of course the capital and operating costs go up a bit. But look what it does to the economics. The profit now went to $1.18 per inlet gallon from 40 cents, okay, at those same conditions. Just because of this new revenue stream up here, all of these short-chain fatty acids, and you can see by themselves they're not that big a contribution. But you'll also notice that the more valuable ones are the larger ones, which are used in things like lubricants, cosmetics. Some of them are even odorants, things like that. There's a lot of uses for these things. And so they're quite valuable because they're really hard to synthesize any other way. So they're actually pretty good. This technology would dominate that market if it went into it. It could easily undercut everyone else. And if we were at the current price of food-grade oil today, which you wouldn't be at food-grade prices, you don't need to clean stuff up that much, and you'd have long-term contracts. But if you were at short-term spot food-grade prices today, with the short-chain fatty acid extraction and making the anode-grade carbon, you would break even today. So that's not bad. Okay. So great, right? We should have these plants in the world, right? Not hydrotreating. So what's the problem? Oh, I was going to show you this stuff, but I'll go on to that. I'll come back to that. We're stuck in the valley of death. So this is the commercialization researcher's worst nightmare. I've been in this valley for 7 years. The problem is I need to scale it up to a demonstration scale size, okay, and then build a commercial plant. The cash flow is longer than 2 years, and venture capitalists don't want to touch it. I need somebody that will commit to a longer cash flow to get it in the market. We've had people that want to do that. They don't have the money. The people with the money haven't wanted to do it. I will tell you that in the last 7 years, I've rarely been more than 90 days away from having my money for 7 years. And it keeps moving. And even today, there's a group right now evaluating it that says, we really like it, we think we're going to do it, we just need a little more time to evaluate the numbers. I'm 90 days away, even as we sit here today, and have been this whole time. This partnership here, this company called Menon International, they're out of San Diego, California. They have a bacteria that is an FDA-approved feedstock. It's aerobic, it's filamentaceous, and it produces triglyceride oils. And so they produce the crude bacteriological oil, and then we process it the rest of the way with our technology. We believe this combination is currently probably the most attractive combination in the world for moving forward, because you can scale this anyway, the bioreactors and everything. So right now, that's probably the best. And putting everything together then, this is the ultimate vision of a biorefinery. Biomass would go into fast pyrolysis and move down this line. Non-edible and edible seed crops would probably be pressed and extracted, although they may also go through fast pyrolysis if you don't want animal feed. Other fatty acid oils like restaurant cooking oil or anything else, animal fats, we've run them all. They just enter later, go to the thermal cracking, you make your main products, but then you can make all this other stuff too from the other things. And some of these are not as far along as the others, but that's kind of the ultimate vision of where a full fatty acid biorefinery would be. It looks very complicated. It is, but think of how complicated a petroleum refinery is. They're very, very complicated, and that's what you're competing against. Right. So, some conclusions. I think it's an attractive method for reducing drop-in replacement fuels in commodity chemicals. It's feedstock flexible, multiple products, increase its fidelity, it's ready for scale up, and we're looking for partners because we're stuck in the valley of death. Right, so hopefully you got some stuff to think about how kind of one of these gets developed and all that. So thank you for your attention, and I'm ready for you to grill me. In the U.S., the federal government policy right now is that global change is a problem, it's a compelling problem, and needs to be addressed immediately. But state governments in the U.S. Have a lot of autonomy in some areas and not in others. So it's a very different system than here. And our state is one of those that's absolutely says, well, global climate change has not been proven, and therefore we shouldn't be jumping the gun to address it. Okay? Yeah, I know. You have to remember, we have a lot of coal companies in our state, and unfortunately they've decided to take the position of the ostrich. It's probably the best way I can put it. But they put out a lot of information, and there's a lot of political spin that goes on in the U.S. A lot of investment in political spin in the U.S. We have these think tank groups where you have people that have absolutely no technical background who are issuing statements about reports and scientific findings and conclusions that have no basis in fact. And it's very common. It's happened a number of times. I think probably the biggest weakness of, I really shouldn't do all this on camera, but the biggest weakness probably of the Obama administration has been their inability to get their message in front of the public first. They're always kind of playing catch up on everything, health care, this issue, you name it. And because of that, these fringe groups and special interest groups have been able to influence the public unduly. I would say probably 20% of the public is totally adamant that global climate change is a myth. Maybe 30%, 20, 30% believe that global climate change is real and urgent, and the rest are completely confused and don't know what to believe. So we have demonstrated most of the bits at about 2 liters an hour. So, you know, it's still small. So what I want to do next, because a big part of our niche that we're going for is jet, it's harder than diesel. I will tell you right now, if I made diesel, I could get farmers to run it tomorrow for no regulation, nothing. They'll put it in their tractors and just try it. They'll try anything. They are risk takers, and they truly believe in renewables, which is ironic, a state dominated by farmers that doesn't believe in global climate change, and the farmers are all doing renewables. But it's good for their business, so that's a whole different reason. But for jet, if you're at 30,000 feet, you really don't want a fuel problem, right? Particularly if you only have 2 engines or something, right? So you have to let engine manufacturers test your product for many, many hours on their engines before they'll put it in the air, and then test it for many, many more in the air. So I want a size where I can produce a tanker car a week. If I can produce a tanker car a week, I can give them enough fuel to test it. Put it through all the paces they want. Prove to themselves that my Jet A is identical to the Jet A they've got. Because they don't care about science. They don't trust it. They don't care what we give them. You can give them the chromatograms. They don't understand them anyways. They don't care. I want to see it in the engine perform. And so that's what you have to do. You actually have to prove it that way. And so that's the next step we want to do, and then move up to the bigger scale from there. If we can get that step, I think we're golden and we're off. And while this is a lesson though, that best technologies don't always get into the marketplace. And if they do, they don't always succeed. Sometimes another technology that isn't quite as good will succeed instead. The big case study on this is when videotapes came out. So VHS was clearly an inferior picture to a Betamax. Sony held the patent on Betamax, and you could only buy them from Sony, and they cost a lot. The inventors of VHS put it on open market, and everybody did it. So it's like Windows is a bad version of the of the Apple operating system that Microsoft invented for Apple for the original Mac. It's clearly a clunkier version. It's not as good, but it's the one that's used all around the world, again, because of open market. Now, there is still hope, because just because you are first, if somebody does have something better, sometimes they still win. Hence, iPhone over BlackBerry, right? BlackBerry, when they came out, right? That was the revolutionary phone. That's the one. BlackBerry was the company. BlackBerry is almost out of business because Apple came in and just blew them out of the water, and so did Samsung, and those two are off and running, right? Okay, so sometimes if you come in with a better product late, you can still win. And that's the argument we're having to make now. We were actually in front of everybody. We were in front of UOP when we were there. And we got stuck in the Grand Canyon, my home state. Yeah. What else? You can ask me about other stuff too, not just about this stuff. For the cracking, I will give you an about range rather than an absolute number. It is in the range of 400 to 450 C. And it varies depending on the specific feedstock, but the range is much tighter than that. Yeah. So not too bad. It's much less severe than hydrocracking in a refinery, for example. And the pressure, it can be very low. It can be atmospheric pressure. You notice not a lot of words, though? This is kind of an American way we do it. Big buttons, pretty lights. I'll put that back up. It doesn't matter which sector you're looking at and which fuel, you're going to have a gap like that. And it's no different in jet fuel. The fact is, we need petroleum for a long time. So I will tell you, fracking is not a bad thing. Bad fracking is a bad thing. Good, responsible fracking is a good thing, because if we run out of petroleum before we fix that gap, can you imagine what world we're going to be living in? The disruptions to basic life all over the world will be absolutely enormous. Our ability to grow food, our ability to produce goods, our ability to have sanitation. There is nothing you can think of that isn't impacted by energy. Energy is the key to society. Our society is built on energy. You can't support 7 billion people without energy, without affordable, reliable energy in the forms that we need to use it. So, in terms of market share, of course, originally we won't make a dent in it. I think with the bacteriological pathway, we have an opportunity to maybe get supply as much as 20% of the world's jet fuel. Because there's not a lot of limits on there, and you can grow a lot more energy in a smaller space with bacteria than you can with crops. That's the whole argument for algae, right? Is that it's energy dense, that the productivity is greater. The advantage with bacteria is you don't have the limitations, the scale-up limitations that people have been finding with algae. Now, Andy's got some ideas on how to fix that too with algae. So by using different algae, and that's great, then that'll be fine. But his algae plants will look a lot like the bacteriological plants when that happens. All of them. I mean, we need them all, right? And so what you want to do is look at what biomass you're talking about and how can we most efficiently use it. Let's not make it do what it can't do, but if we can make it do what it does well, that would be good. Having said that, a lot of us researchers make our living inventing ways to make them do things they don't do. But then they can do them, and that's fine. So there's nothing wrong with exploring all kinds of ways to try to use them and exploit them. But when you're looking at what should we do for the next decade, because it's 7 to 20 years to develop a process from concept to commercial. 7 is really low. Most of them are near 20 in the process industries. So what do we do in the meantime? Well, you use it the best way you can. Right now, if you've got a lot of residual leftover biomass, you're probably best using it for power generation and using the char for soil amendments. If you've got other wastes, you may be able to make a syngas efficiently out of them. So a lot of people are doing that with sewage waste and things, making syngas out of them to use that way. So I think it's, you have to kind of look at each one to try to decide. And of course we need food too. But again, food, don't get sucked into that argument that it's food or fuel. It isn't. It's like frack or no frack. It's always more complicated than you think it is. There's always nuances, and the market's dynamic. It's not static. So there are ways to accommodate fuel crops into the agricultural rotation cycles and have them work. So for example, I have a colleague at North Dakota State University who's in plant sciences, and she just recently completed a study to look at doing relay cropping in North Dakota. Now, relay crop means that after you harvest the first crop, you go ahead and plant let's say you plant the second crop before you harvest the first crop. And then you harvest the first and then the second. And if the plants are, big and then small, and the lighting is right and the timing is right, you can do that. You can relay crop them. Another way to do it is you can overwinter crops. So where we are, farmers can't get into the field until about the 1st of May. But they could start growing things sometime in April. So if you can plant a crop in the winter or in the fall before the ground freezes, that will just stay dormant and then emerge just as spring starts. You can gain a whole month on that winter crop, harvest it, and plant another one and still get in a relatively short growing season. So there's a lot of things like that that agronomists are looking at to try to make that work. So it's not yes or no, it's yes and yes. We just have to find out how to do it more sophisticated. That's why engineers get the big money to figure those things out. Apparently agronomists too. Well, if you're farmers in the developed world, like in the US, the farmers are very sophisticated. The last thing they want to do is deplete their soil. They do carbon balances, nitrogen balances, phosphorus balances, you name it, they're evaluating their fields all the time. The last thing they're going to do is salt that field, screw that field up, just to do it, farm it out, which is how farming practices happened, in Europe and everywhere else until about 200 years or so ago. And still happens in some developing countries that do not yet have good enough farming practices. But with modern farming practices, I think that concern is pretty minimal. So if you want to crack a long-chain hydrocarbon and make shorter chain hydrocarbons, it actually takes pretty intense conditions. As you know, the temperatures are high. They're higher than we're talking about. And you also need pretty high pressures, hydrogen pressures, to do that. And it has to be facilitated with a catalyst. Until they developed catalytic cracking in the 50s, it was not feasible to just thermally crack heavy hydrocarbons into middle distillates. It wasn't done anywhere in the world. Refiners didn't do it. So the prevailing opinion has always been you catalytically crack. If you're going to crack, you need a catalyst, because in petroleum you always did. I believed it as well in 2003, but I had a student that I didn't trust with the catalyst yet, so I started him on non-catalytic cracking. Guy needed to get a degree, get a job, we'll get him through. The next student can put the catalyst in the bed, right? You've never done that, I'm sure, with any grad student. I'm sure there's nobody here. I hope there's nobody here that's in that boat. But it turned out, just by serendipitous luck, as we were exploring cracking conditions, and we had no idea what conditions. So I had him just surveying every 25 degrees. Try it, see what we get. And suddenly magic occurred. No cracking, no cracking, no cracking, no cracking. Boom! This is great. Next step up, coke everywhere. But there's a range in which, a sweet spot, in which this works beautifully. Then I began looking at those catalytic cracking papers of soybean and all these oils that have been in the literature since the 60s. And I started looking at them more carefully, and almost to a paper. Every one of them was a lab test, and here's how they did it. They put oil in a beaker at the bottom. They heated it up and vaporized the oil, and as it flowed through the catalyst bed, it came out and they evaluated the products, okay? Now, the temperatures at which they operated that unit were below the boiling point of the oils. What was happening in the oil? It was cracking. The vaporization was cracking, and they saw it as boiling. But it wasn't boiling, it was cracking. These oils crack so easily. If you've ever run a deep fat fryer, you know this, right? If you ever worked in a fast food restaurant that makes chips, how long will the oil last before it's rancid and black and nasty? That's cracking. That's cracking and making the tarry stuff. You can't keep them from cracking. You can't do a full distillation curve to the boiling point because they crack before they get there. So all those experiments we're doing is they were non-catalytically cracking and then doing secondary reactions through the catalyst. They didn't know that's what they were doing. That happens. There's a lot of peer review out there like that you can't just take at face value. Sometimes you have to look deeper at it. I had a student that didn't believe you couldn't decarboxylate. He didn't believe the literature on decarboxylation of short-chain fatty acids. The prevailing wisdom is you need something like palladium or platinum on something like carbon to do those reactions, right? And that's what hydrotreaters do. He said, no, he said, I don't believe it. He says, I think we can do it with nickel. And he went and showed me in the literature all the data that they had where they'd done comparative tests. And he said, they did this wrong, they did this wrong. This was because of analysis. They didn't analyze correctly. This one's wrong. I think we can do it. I said, go for it. Make my day. Prove it. And he did. And so we decarboxylate over nickel. We don't do it over palladium. So that reduces the cost of one of these plants just that, the capital cost by a third by doing that.
I think we'll call that a day. Thank you very much again, Wayne, for coming in and taking the time to do that, especially at such short notice. So if you'd like to give your appreciation again.